Alright, today's video is about Cartesian and polar coordinates. So let's get started. So we're going to talk about what those are first of all, and then we're also going to talk about how to convert between them. So first are our Cartesian coordinates, and a set of Cartesian coordinates is a point on our Cartesian plane. And this point will have an x-coordinate and a y-coordinate. This is probably what you're most familiar with, if you've taken some math classes in at least high school probably. But this is more of a review, I guess. So yeah, the Cartesian plane has an x-axis, which is the horizontal axis, and a y-axis, which is the vertical axis, and these are located at y equals 0 and x equals 0, respectively. And a point can be in one of four quadrants, depending on what sides of the axes it falls on, unless it's on an axis, of course, in which case it's not in any quadrant, really. So quadrant 1 is this top right one, and it's when both the x and y coordinate are positive. Quadrant 2 is the x coordinate is negative, but the y coordinate is still positive because it's above the x-axis, but to the left of the y-axis. Quadrant 3, now we're below the x-axis, which means now we both our x and y coordinate are negative. And lastly is quadrant 4, so we're back to the right of the y-axis, so it's a positive x coordinate again, but we still have the negative y coordinate. So now we talk about our polar coordinates. So a set of polar coordinates, which we may refer to as a vector for our purposes here. It has a magnitude, or a distance from a reference point, and a direction, which is the counterclockwise angle it forms with a reference direction. If you're doing it clockwise instead for your reference direction, from your reference direction, it'll be negative. And this angle, it could be in degrees with the degree symbol or in radians. We're going to use degrees here because I think that's more easy to understand, but radians also works too. And the important thing to note for that is that 180 degrees is equal to pi radians. And another important thing is, when you're plugging this into a calculator, is to make sure you actually know what mode your calculator is in, because it has a degrees and a radian mode. So definitely check on that before you plug any numbers in. And another important note is that once you go 360 degrees from a direction, that's a full rotation, which will mean you're just right back to where you started. And that's, just basics of circles. But the point of that is if you have an angle bigger than 360 degrees, just know that you don't have to plug in that number. If you know what value it's equal to on the less than 360, you can just plug that in instead. So this picture here shows an example of this circle here, basically. So the vector here has a polar coordinates 4 and then 60 degrees. So I guess it'd be easier if you show the cursor. So if we go here, the magnitude's 4 on this. So yeah, radius from this center is 4, and the reference direction here is going to the east here where these numbers are. So it's 60 degrees up from that. So right here is that where that reference direction is. So something you may be asking is why you would want to convert between these in the first place. And the main reason is that I can give you is if you're given multiple sets of polar coordinates and you're told to add them together, then the easiest way to do that would be to first convert them to Cartesian form. So the process for doing that is, of course, converting all those polar coordinates to Cartesian, and then adding all the x-coordinates of those Cartesian coordinates together, and then doing the same for the y. And then after you have those all added together, converting those Cartesian coordinates back to the polar to have your result. So yeah, a way to think about it is like a triangle, and it'll come out here again. So we have our cursor. So yeah, all four of these values you can combine them to basically form a right triangle. The important note is that the reference direction in this case would be the closest axis, meaning that the angle wouldn't exceed 90 degrees, because otherwise you couldn't form a triangle with it. So yeah, looking at our triangle here, we have these two sides here, these that are perpendicular, those are x and y, representing our x and y. And they're perpendicular, so they form this right angle, making our right triangle. And then this point up here represents our xy. But it can also represent our polar coordinates with the magnitude, which is represented by r here, which is this diagonal line connecting the two perpendicular sides of the triangle together. And then also our angle, of course, from the reference direction, which depending on how we're doing this, this may not actually be our full angle, but it'll be part of it at least. The rest of it, like if there's something down here, then you just add that. But this is, I think, easier, best way to visualize it at least. So now with that visual in our heads, we can start talking about converting from Cartesian to polar. So we assume at this point that we have both our x and y coordinate, and that we're trying to find our r, which is our magnitude, and then our angle in degrees. So to find the r, or the magnitude, if you notice that since it was a right triangle and the r is of the hypotenuse, then you just use simple Pythagorean theorem. Square root of x squared plus y squared will give us our magnitude, and then our angle is the inverse tangent of y over x from basic trig, because normally tangent theta equals y over x, and if you cancel out the inverse tangent, then you'll get this. So of course the other way is possible too, and in this case, of course, we assume we have our magnitude and our angle. So, and we're trying to get our x and y. So to get the x, you multiply the magnitude times the cosine of the angle. And then for y, it's the same thing, except instead of the cosine, you just do the sine of the angle. So with all that brings us to our practice. The first one, pretty simple, is just converting some polar coordinates to Cartesian. And once you get those Cartesian coordinates, you should be able to tell what quadrant of the plane the point is in. And the second one is maybe more of a real world problem. Maybe probably not. I don't think something like this would come up, but just for fun. About an airplane pilot basically being given two instructions here that are like polar coordinates, and trying to condense how we could condense that down to a single instruction that the pilot could have been given instead, assuming it wouldn't cause any issues, of course. So I'm going to start showing the solutions to these here in a second. So if you'd like to solve them on your own and then compare with mine, now would be the time to do that, because we will start looking at the solutions in 3, 2, and 1. All right. So our number 1 here, pretty simple. We're going to get our Cartesian coordinates using those formulas we showed earlier about multiplying the magnitude by either the cosine or the sine of the angle, and that'll leave us with both of our coordinates here, in this case, being negative. So that would mean that the point is in quadrant 3. So that brings us on to our second one, which is a little bit more involved. So first we have to convert both our vectors, their polar coordinates, to Cartesian coordinates. So, and that's just the same formulas from above, multiplying the magnitude by either the cosine or the sine of the given angle. So yeah, hopefully no problem there. Again, remember to make sure your calculator is in degrees mode. If your values aren't lining up with these, then that's probably why. And then the next step would be to sum the coordinates of the vectors. So we have the x, writing the x coordinates of each vector and the y coordinates of each vector. That's giving us our resultant vector, or coordinates that will become our vector. And then lastly, convert that back to polar using the formulas we showed from earlier, where the r is the square root of the x squared plus the y squared from our Pythagorean theorem, and then our theta is our inverse tangent of y over x. And that leaves us with that the pilot should fly, apparently they should fly 1,007 miles about at about 68-degree angle, basically. from the north. So yeah, hopefully that all made sense. If you have any questions or feedback, feel free to leave them in the comments. I'll see you all next time.